This idea that 400,000 people couldn't keep a secret is such a ridiculous comment to make because it doesn't even address the problems. Yes, 400,000 people could if they were asked to do so, but they were never asked to do so. The people involved, who were US Air Force personnel, had security clearances, they honored to the letter. They were patriotic and honorable people. If they were told not to discuss something, they wouldn't discuss it. End of story. It's the follow-on from that famous World War II placard, or poster we had in the UK. Loose lips cost lives. Let's not forget that people are patriotic. People like to do the right thing by their colleagues, by their friends, by their country. That's what being patriotic means, doing the right thing by your country. If they were asked to do something, they would do it to the best of their ability, which is what they did. And all those 400,000 people were working to the best of their ability to do what President John Kennedy had said they should do back in 1961, land a man on the moon before the decade is out. They were doing their best to achieve that. How was anybody to know that it wasn't possible? That wasn't what they were investigating. They were investigating getting to the moon and creating the equipment and the backups needed, all the rockets, the landers, the control centers, to do that. That's what they were doing. The fact that it didn't happen was a closely guarded secret, certainly from them. So 400,000 people didn't need to keep a secret. They had no secret to keep, nor did the 2 million other people closely associated with those 400,000 people, their families and close friends. That's a large proportion of the scientific community in America at the time. They were doing the best job they could. End of story.
I was watching a new method to measure the amount of evaporation off of a lake or whatever, right? And sunlight itself creates an evaporation. And I was looking at this one and it was showing breaking down the molecules. It's a photometric evaporation is what you're looking at in the thing. It's not just evaporation from thermal evaporation. This is all part of the same as outgassing. It's the same as outgassing. So now you have sunlight, when it's hitting a surface, is physically breaking down the molecules so that they evaporate. And that's without any added heat or anything else. And you combine that and then put it into a vacuum where the molecules can be more active. They're going to fly off quicker. So that's probably how you get a little bit of additional cold welding when you don't think you should be having cold welding when you're sitting in space. Yeah. Because if the sunlight's hitting it, it's breaking down, actually physically breaking down a solid material like a metal. It's the photometric charge to that is creating those molecules to break down faster and more rapidly. Most of the examples I'm looking at here are based on water, where you can control the water temperature and the normal rate of evaporation. And of course, we have that with daytime and nighttime. But evaporation doesn't stop just because it's nighttime. Otherwise, you wouldn't have mist on the lake in the morning before the sun comes up. But then you see it accelerate when the sun hits it. The sun actually helps to get rid of fog and mist because it's splitting those molecules apart quicker than even the temperature is doing. That's a prime example of what we're talking about here. Now, when you're in space, you're receiving 100% of that sunlight. The UV, everything else of that sunlight. It's not being diffused either by the atmosphere, right? Not being blocked by the atmosphere, and it's not being diffused by the atmosphere. That photometric evaporation is going to affect any materials there. And when you get a certain level of vacuum on top of that, of course you're going to have an effect of cold welding. It's going to be amplified on that. I don't care what the cameras were being protected by. We looked at the examples of the Mylar that they say they were testing on the ISS and stuff like that, and it's completely breaking down. Well, they are learning what is causing that, and this is part of it.
Yeah, it's a very good point you make about that evaporation is very similar, if not identical, to outgassing.
It's the same effect. One's a hell of a lot slower because you're in a pressurized environment on the Earth, but you have all of these other stuff like sunlight itself is in addition to that evaporation or outgassing. Yeah. If you leave anything on the Earth long enough, if you leave two pieces of lead together on the Earth, they will cold weld themselves together. You can accelerate it by squeezing them together. But if you simply sit there, they're going to outgas. It might take 1,000 years to do it, but it's going to happen. You stick it in the ground, in the earth, and you squeeze it together and add a little more heat, and they bond together quite quickly. Well, you put them in a vacuum, and you've seen examples of where they simply can touch it and it sticks. It reacts that quickly on certain materials, right? Even the ISS, when they're using their tools on the outside, they put the screw gun up to something and take it, and it's stuck to it right away. I mean, they even show that. The outgassing is that quick. Well, how are you going to undo that screw? Because it has cold welded itself to the material itself. It's not coming out of there. It's no longer a screw. It's just one solid material.
Yeah, well, what happens if you do that in assembling? You know, I look at it this way. Let's take a look at this Gateway lunar station. Now, when they're assembling that, they're going to be putting nuts and bolts together. So that means that as soon as they go to crank these bolts and nuts, if they're not treated with some chemical that I have no idea what they would treat it with, like they say they do, the second that gun touches that nut to screw it in, that's the end of it. It's welded there, and they're not going to be able to screw it in any further.
Good point.
As soon as they create the friction with it, it's going to accelerate the effect.
That's it. Yeah, it's finished. It's welded.
And of course, the Gateway is allegedly going to be assembled, which is in lunar orbit, where the vacuum levels are far higher than they are in Earth orbit. Earth orbit is torr 10 to the minus 6, possibly. Lunar orbit is torr 10 to the minus 12. That means that any effect of the vacuum on the material is going to be much faster. As you say, just adding a wee bit of heat by using a mechanical drill to put the screws into place, it's going to add that heat, increase the level of cold welding, and the whole thing will grind to a halt. I wonder if NASA have even thought of this as a problem of assembling items in space. They say, well, we assembled the International Space Station. How hard can it be? Actually, very hard indeed. In lunar orbit, that's the difference. The two are quite different.
Well, it brings you to another problem every time they dock and undock. How's Musk going to be able to refuel? I mean, they got to lock those things in there to transfer the fuel, right? They're going to cold weld themselves together. There's going to be a problem with that. And if they can't undock from one another, how can they return from anything? If you dock onto something and you can't release again, it's cold welded together.
It's funny you said that, because in one of the diagrams, they're showing this CGI version of how this is going to be accomplished. And what happens is the tanker comes and it drops down onto Starship to be refueled. Then this little base comes up and joins with it. It refuels, but they never show it decoupling. They show this arm come up and it goes like this, and it couples to the ship. And the ship and the tanker now are all one, heading off to the moon. Well, yeah, maybe that's why, because they can't get them apart.
Maybe that's what happened to Surveyor 1. Encountered alien stuff out there, and it was reporting on it, and when it locked onto it, it was assimilated. I know our viewers like a little humor every now and again. I'm thinking that pretty much everything that we do in space has got a bit of mystery to it, if not fantasy. And it's becoming more and more apparent every time we look into a particular subject and find the problems. Everything in space seems to have a problem. It's not just straightforward. It's not the same as operating on Earth. You're in a continuous, deadly environment that humans are not welcome in. It doesn't matter. The slightest little mistake, vacuum, a CME can take you out in a heartbeat. Any malfunction from life support systems of any kind, you're simply dead. And there is no escaping it. They don't have escape pods. We're not talking James Bond Jaws when they're re-entering in, but all of that stuff, I mean, he survives everything. I mean, that's the fantasy that NASA wants to keep us in, that they project these images and they want us to believe it. Well, it's no different than the movie industry. But do you believe that Jaws re-entered into space and landed in whatever vehicle he had left? Because there was nothing left of whatever he was doing, without an atmosphere, without anything.
Just minor details, aren't they, which can be ignored because people don't need to have them. They're not part of the storyline.
NASA would like us to believe is that these things are happening and functioning. We can communicate. There's never an interruption. It doesn't matter what electromagnetic field is flying around out there. That doesn't seem to bother us. None of that stuff. The vacuum doesn't bother us. The consumables that it must take to be in space. You have to have a controlled environment all the time. The heating and cooling alone. And then they're going to make oxygen from water. Well, how the hell do you get all that water up there when Musk can't even carry enough fuel on an empty machine to make it to space? How the hell is that going to happen? How are you going to add water to it? Water weighs a bit of weight. I mean, if they started telling us that they're evaporating water on Earth and letting it rise up, and then when it makes it to space, condensing it back again, so it makes the trip on its own, that would be interesting. By the way, NASA, now that I mentioned it, go ahead and do it.
There's your challenge, NASA.
Yeah, there's a challenge. Just evaporate water and make it condense on an object at the Kármán line so you can take it into space.
They're going to have a problem again with the gateway station, because what's going to happen is they're using some kind of electrolysis in the water to make the oxygen. And then what happens is now it's going to reclaim the oxygen in through the environmental system, and it's going to turn that back into water again. But you're only going to get so much water back. You're going to hardly get anything back. So eventually it's a closed loop system. The system is unsustainable because you're not getting back what you're putting into it. So eventually the water is going to run dry. So where are you going to be getting that water from? It has to be ferried up there with another spaceship.
Or 2.
Or 3, or 15, or now, according to Thunderfoot, it's 30.
Yeah, 30 spaceships. I mean, that's what VonBraun was saying 60-odd years ago. We need something the size of the Empire State Building, weighing 800,000 tons. Seems a bit ridiculous.
And 11 launches and stuff like that. He was doing that at the same time.
Talking of VonBraun, as we were, it's an interesting film I just watched about how the V2 rocket created the turbo engine to drive the fuel and the oxidizer into the rocket motor itself. And they did it using a turbo pump, which is a very fast operating piece of equipment. But how did they start the turbo pump? It didn't use petrol, as most turbo pumps would use, like firefighters use turbo pumps to pump water. How did the V2 rocket get a turbo pump started that was powerful enough to drive the fuel and the oxidizer in? And the answer, which I was quite surprised at, was steam, because that started the blades of the turbo pumps spinning, and they were created in such a way that it would drive the turbo pump. Now, they used steam. How did they produce the steam to drive the turbo pump? They used hydrogen peroxide and sodium permanganate. If you add those two together, it produces steam. If you use potassium permanganate, it also produces steam, but not at the right temperature. Hence, sodium permanganate was used on the V2 rockets. This is back in 1942, 1943. They were working that one out. So presumably the same applies to the Saturn V rocket. How did they get the turbo pump started? Did VonBraun use his original idea? Because he designed the V2 rocket. He also designed the Saturn V rocket. Did he use the original idea of using hydrogen peroxide, H2O2, plus sodium or potassium permanganate to create the steam? Oh, it's a brilliant idea to get the steam powerful enough and hot enough in an enclosed environment, i.e. a rocket. I'd always been told that it was using a very powerful engine, like a V12 motor engine. Apparently not. It was using two chemicals which were driven together within the rocket to produce the steam, to start the turbo pump, which it would do. And the blades of the turbo pump were built or designed in such a way that as the steam went through one way, it was then diverted back again, because the steam would just go in a straight line. If you divert it back, it will drive a second turbo pump blade. It's a brilliant piece of design in the 1940s. So maybe he used the same thing. I don't know. I'd be interested to check it out, because it's something that it's never occurred to me. There are films on how do you start a Saturn V rocket? How do you launch it? Maybe it'll be in that. But if it uses hydrogen peroxide and sodium or potassium permanganate as the agent to create the steam, a simple experiment, just add those two together. Whoops, lots of steam.
So yeah, that's dangerous stuff.
Yeah, it is. It is dangerous. You've got to control it. It has its uses if you know how to use it and control it. You've got to control it. Now, here's a question. We were looking at the cooling of the command module in space, all right? The command module, when it's traveling from Earth to the moon, we're told, allegedly traveling, we're told was attached to the service module by these bolts through the heat shield, which obviously didn't affect it because you put a big hole through the heat shield and you've got to seal them. Anyway, all the cooling of the command module in space was apparently done using equipment and using stuff that was contained in the service module, which is quite big. Now, here's the question. How did the lunar module on the lunar surface keep cool if it didn't have access to a service module to provide the necessary raw materials to keep it cool?
Well, they had a sublimator on the LEM, and I've showed some videos before of how they did that. They have a whole system. No, but they do. They have a whole system.
Okay, but how much water would be required to be carried to remove the specific amount of heat that is generated inside the lunar lander?
They also had liquid glycol tubes as well going around there to cool it.
There's a couple of things about that machine. First of all, it's sitting with one side in the sun. It's not rotating. Number one. Second of all, the door is wide open. Thirdly, they claim all the power is shut down on it. How much power does that TV camera draw?
Those cameras draw 2 amps.
Yeah. Well, they're sitting there. They got a TV camera. Well, that's hooked up. You can see the cable hooked up to the LEM. So it's drawing its battery power away. And the biggest thing I have is when they repressurize it, it is going to freeze that thing down to probably 190 degrees Celsius, minus 190 Celsius. When they repressurize it, you're taking compressed gases and expanding it in there. You're going to freeze everything solid when they get in and repressurize that machine. When they do all of those tests on Earth, they just use atmospheric pressure, not pressurized, when they're bringing the pressure back up in any vacuum chamber. Now, if you took your vacuum chamber, Robert, and you took compressed air and introduced that into the chamber after you take the vacuum down and repressurize it, look at how fast you can freeze that can.
Oh, yeah, that's right, too. Yes. Yeah, no,
Okay.
I did that.
But I'm saying if you take and the air that you're putting back in the chamber is compressed air, because that's what they would have, it's going to expand into that space and it's going to absorb all of the heat. And when you're talking what they're doing in that size of a space, you're going to freeze everything down. Now, of course, they're in there at the time. And let's hope that their spacesuit is able to control that temperature so they don't freeze. They only had, 6 hours or whatever that they had to, change their diapers, have something to eat, recharge all of this stuff, and get everything ready for the next EVA. But they're not going to be able to get out of their spacesuits when they're inside that craft until it warms up. Now, if they're sitting there saying, we have heaters to compensate for that amount of freezing that's contained in those chambers, how much more energy is that? Huge. Nobody ever talks about it. The reason why NASA never comments on any of this stuff is they go on the basis is you can't catch a fish if it doesn't open its mouth. That's the basis that NASA works on. And we see that in the comments. We make particular statements out there. Nobody comments on it because they simply can't. And like I said, you can't catch a fish if it doesn't open its mouth.
In the last video, I put a question out there and I said, how can Jeff Bezos fish an F1 engine out of the Atlantic Ocean that has been down there for 55 years at 14,000 some odd feet down in salt water? He brings it up, they refurbish it, and they fire up the gas chamber, and guess what? It works. So why can't NASA do the same thing? They don't have to go digging any engines up. They have them in their museum. Not one person has ever asked a question or posted a question on that. And it's the same thing when we talk about some type of radiation. You'll never hear it. What about the spacesuits in the Sandusky chamber? Nobody talks about that either.
Because they can't. Those spacesuits were never tested in the Sandusky chamber. Just in case anybody's wondering where the Sandusky chamber is, it's part of the Glenn Research Center at Ohio, near Wright-Patterson Air Force Base, if anybody wants to know. You've got all these anomalies. I mean, these are real anomalies. How did this happen? You ask a simple question, which is trying to encourage people to give information that will help us answer the question, but nobody ever does. Nobody can ever come up with the answer.
Well, here's the other thing that we haven't discussed either. When you heat and cool metals, they expand and contract. And when you're using a different combination of metals, they expand and contract at different rates. And now we're not talking about a few degrees in temperature. I mean, that's one of the biggest things in the automotive industry. They're using metals, and then now they have to match the paint to expand and contract with the heat as the sun hits it. Otherwise, the paint's going to crack all up if it expands at a different rate than the metal does. That's also with ceramic finishes are exactly the same way. You will get a tortoise effect on it if your ceramic coating expands and contracts at a different rate than the paint does. I mean, It's all this technical stuff. Well, now we're talking about a 500 degree range minimum and incredibly precise seals to make that door seal. Simple as that. You close that door and you go from whatever temperature plus 270. And if you're pressurizing that vehicle and you're going to bring it down to minus 190 Celsius, man, those door seals are not going to work. I'm sorry. All different kinds of stuff is going to happen to it. And of course, that's the same thing with the cameras, right?
Of course it is.
What they claim that it takes a year to produce a camera, and the precision of the gearing and the shutters themselves are so thin and precise, it's unbelievable. And the speed that they're operating at. And they're very sensitive. The speed they operate is very sensitive to temperature. Anybody that uses a film camera professionally knows bloody well, like anybody that was doing weddings or anything else in the 60s and 70s, right? And they're using a Hasselblad camera. They would tell you in the evening shots, they would have to change the parameters of that camera to work properly to capture a decent shot. And you know that yourself.
Definitely, yeah.
You're out on a nice hot sunny day into an evening shot in a thing over the course of a day. You're changing all the equipment up all the time to match your environment. And that's only a couple of degrees.
Yeah, it is. Not very much temperature range at all. But on the moon, as you said, the 500 degree Fahrenheit temperature difference between sunlight and shade. Now, an excuse is often made that they allegedly landed the Apollo modules when the sun was low on the horizon, i.e. equivalent to dawn on Earth. No, it doesn't work that way on the moon. On the moon, as soon as sunlight hits an object, it immediately starts heating it up. And that was demonstrated conclusively in that famous story of the shuttle astronauts who said their hands got very cold indeed when they went into the shadow of the Earth, out of sunlight. And NASA didn't believe them and said, go and take the temperature, we'll find out. So they did. And the report was the temperature coming out of the shadow of the Earth on the space shuttle increased to over 100 degrees Fahrenheit within a few minutes, i.e. very fast.
Well, we covered a little bit on the surface of the moon before, and I know they put up some PDF files on it on how the temperature rises, because what they're using is they're using Earth's parameters. But the moon, if you're in sunlight, it's irrelevant. If you're in space, you're in sunlight. It doesn't matter whether you're on the moon or not. You are in space. When you're on Earth and the morning sun comes up, it takes a while for it to warm up because it's diffusing through the atmosphere at an angle so that the ground is not hitting that direct impact of that sunlight. On the moon, you're either in sunlight or you're not. You don't have to be on the moon, you're just in space. You're either in sunlight or you're not. Simple as that. Standing on the moon is no different. So it's going to heat up very rapidly. And they have tried to create documents saying, oh, it just heats up slowly, and they have gradients on there. You can see it from the stuff. And they only came out with those documents after we made the first comment on it. It was 3 or 4 years ago. And they now produce the documents. And there's no sense of anybody downloading them because it's bullshit.
Yeah, exactly. It's been proven for years that sunlight in space acts very fast. Because space has no temperature until you put an object in space to have a temperature, or the moon, or a spaceship, then it has a temperature.
And you're getting 100% of that sunlight.
Yeah.
You're getting all the UV, all the radiation, all the ultraviolet, infrared, everything else, plus 100% of the white sunlight. We did a video on that showing the percentages there. Basically, half the white sunlight, you're missing it. About 90% of the UV, and is pretty close to the same as that as far as the infrared, is being blocked just by the atmosphere. And then, of course, our ozone layer is blocking even more of the UV to control it even further. People don't understand that when they're in the full impact. If they were exposed to the full impact of that, You wouldn't be able to stand, your skin would burn within minutes from that sunlight.
It burns on Earth if you spend too long outside.
Well, we did that, and people that go up to observe the flamingos have to completely cover their skin because of the sunlight. At that altitude, that lake is what, 12 or 13,000 feet up? But the atmosphere is just thin enough. It's not blocking anything. Like no other species up there other than the pink flamingos. And then we're making a joke that's why the flamingos were pink, because that's where they go to get the color kind of stuff. But that's how dangerous our own environment is to us. We are restricted basically within, 10 or 12,000 foot range from sea level.
That's only 2 miles up.
Of course, if we didn't have any of our technology, we would be restricted to within the temperature ranges around the equator. We'd have to find a modified, more temperate zone where we could exist. And that's how we initially existed until we learned how to clothe ourselves and heat and feed ourselves in those different environments. And just because we can do that on Earth for a small period of time, we can be at the North Pole or the South Pole and survive, doesn't mean we can survive in space.
That's why I keep saying we're very delicate little creatures, us humans. We've got to be protected from the dangers of space. Space is a very dangerous place for humans. We're not designed to be in space. We're designed to be here on Earth at sea level or slightly above it, because we know how to protect ourselves, because we've got so much atmosphere above us, 50, 60 miles of atmosphere, depending on how you measure it. The Kármán line says it's 60 miles. That's named after Theodore von Kármán, who was a NASA scientist, determined the Kármán line. And that's where spacecraft returning from lunar orbit at 25,000 miles an hour hit the atmosphere, 60 miles up. And then they have to slow down because it's an immense amount of energy. And you've got to have protection from that. I mean, the heat of re-entry is really quite severe. At least NASA knew they had to protect the spacecraft with this heat shield that they developed, which seemed to work for Apollo. It seems to work for the space shuttle and for craft returning from the International Space Station. But can it protect against spacecraft with humans inside returning from lunar orbit, where the speed is much higher, the temperatures are much higher, and the distance to slow down is much longer? It's well over 1,000 miles of travel through the atmosphere to slow down. That produces a vast amount of heat.
Like I said, they're still having trouble with Orion from 2014 on the testing, right?
Yep.
In particular, right around the mounting things there. And I can't think of the name of the other one that was like the space shuttle. It flies back in, right? It was a return vehicle that would fly back in and land. And I kept looking at the design of it. It doesn't even have a front wheel on the thing. It just has a drag thing on it because, of course, you can't have the hydraulics and you can't have, rubber tires in space and all of that stuff.
Yeah.
That it was flying back in. That one I think is being canceled. For the life of me, I can't remember the name of it because it's not making a lot of news. And nobody is showing us that it can handle anywhere near the temperatures re-entry coming back from the moon does. Because they're only going into low Earth orbit and having that problem coming back. That's nowhere near the temperatures of re-entry from traveling farther out.
It's about double. Coming back from lunar orbit, it's about double the speed of coming back from low Earth orbit. 18,000 miles an hour low Earth orbit entry speed, 25,000 miles an hour entry speed from lunar orbit. Twice the energy needs to be dissipated. It's a major problem. I don't think anybody's solved it yet.
I guess it's the same thing as if you hold your breath to the very limit you can hold your breath, and then somebody says, now double that time. You can't do it. Take your little Toyota Corolla out and hit the gas pedal and it goes this fast. And then somebody says, oh, just double it. That's what they're doing because they're already at their maximum capabilities and they need to at least double that. It's the same as the consumables. You don't hear people talking about the amount of consumables that have to be on a spacecraft to keep people alive. It means you have to have a support vehicle all the time. Currently, what is happening at the ISS, the little Starliner got those astronauts up to the ISS. They have a problem with the machine. And these guys are saying, oh, we're going to fly it back even though there's a problem. It's got leaks everywhere. Everything is leaking. It's got damage to the heat shields. It's got all kinds of stuff that they're talking about. And these guys say, oh, yeah, we'll just fly it back. There's not a problem.